Great. Ah, okay. Amazing. Where do I need to point this to? Here? Wait, I'm confused. Okay. All right. Yeah. Thanks for the thanks for the organizer for the opportunity to present this tutorial on representation theory for quantum computing, and I hope you guys enjoy. So this is a little bit of the outline for today's talk. We are gonna introduce groups and representations and also algebras. We're gonna use two main groups to exemplify and instantiate representation theory. These are the symmetric group and the unitary group. And the reasons why we choose these two groups will become clear. They are of central importance to quantum information, and they have also a kind of a sort of dual or complementary representation theory, which is embodied by a phenomenon called the Schur-Weil duality, which we will finish presenting and probably wrap up there. Okay, so a quantum computer is a many-body quantum system that's ideally closed and over which we can implement arbitrary sequence of polynomially many local operations. We believe that the power of polynomially sized quantum circuits is strictly larger than that of classical polynomially sized classical circuits, and we attend quantum computing conference to argue about potential quantum speedups and applications. So quantum states are vectors in this tensor product Hilbert space of like n qubits, right? So 2 to the n is a dimension, and quantum circuits are d times d, so exponentially large unitary matrices. So I ask the question, is quantum computing just high-dimensional linear algebra? And in my opinion, it's a little bit more than that, because we don't really care for all high-dimensional linear transformations, but instead for certain very structured subsets that arise from embedding, for example, algebraic structures like groups, rings, algebras, the ones that we will discuss soon, as subsets, as very structured subsets of this totality of high-dimensional linear transformations. So this is kind of the introduction to representation theory, which is a bridge between these algebraic structures and vector spaces and linear operators. In a sense, it's an embedding of these structures. So to begin, let's define a group as a set G with an associative operation circ that takes two elements of the set and produces a new one. Again, the operation is associative, so it doesn't matter if I have to combine three elements, I can combine the first two and then the third, or the second two and then the first one. The set G has an identity element in the sense that it's an identity in the sense that the product of this identity with any element returns this other any element G, and every element has an inverse. So every G has a G minus 1 such that when I take the product, I get the identity element. As an example of a group, we can consider the symmetric group, which is the set of bijections from the set of n elements to itself. So here, I think it's worth kind of a little bit of drawings. They will come soon, but like, suppose I have n elements, okay. Say, n elements, and I want to produce a bijection. The question is, how many bijections are there? I can just choose to send the first one to n different places. I choose the second one. Once I fix this one, let's say I choose this one. I have n-1 choices for this one, and so on, n-2, and so on. And for this one, I don't have a choice. So the number of bijections, so basically, so like this, the order of Sn is n-1 all the way to 2, which is n factorial. And also, like, I can visualize the bijections with these kind of diagrams where I kind of put, for example, let me just draw a single bijection. It could be kind of this one. Or instead, I could just swap the first two. So these are elements of this symmetric group. And yeah, so they are depicted by these diagrams. I can also, another interesting way of, or like common way of notation is like to have like an order. First you put like the n elements, and here you put where each element is sent. So in this case, 1 is sent to 2, 2 is sent to 1, and the rest are sent to itself. And yeah, so with this we can move on. So I'll explain here. This is the way I'm using the notation here. The diagrams are, I'm just like writing. Please stop me because this is, we'll come back to this all the time. So for example, the symmetric group on 3 elements, there are 6 ways or 6 bijections from the set of 3 elements to itself. First, the identity one, then the one that permutes the first 2. When I write this kind of empty bracket, it means that the first element goes to the first, the second element goes to the third, and the third goes to the third. So this is typically when I write this kind of bracketed things are called cycles. And if I all 1 cycles, I just don't write. Okay. So I hope all of this. So the symmetric group on 3 elements has an identity, which are 3 1 cycles. Then it has like these elements 1, 2. That's just a transposition, 1 and 2. There are 3 transpositions, and then there are 2 3 cycles. Okay. No questions? Yeah, okay, that's the set. Okay, I just described the set with like permutations, but now we need to kind of check that this is a group indeed under the operation of composition of diagrams. Okay, so like if I take the permutation 2 3 and 1 2, I stack them together and I just connect the dots. I get the 1 2 3. It's easy to see. Like you start from the first guy, just goes down, but then it swaps with 2, so it ends up at 2. So the thing on the right is saying that 1 goes to 2, 2 goes to 3, and 3 goes to 1. So it's a group because like you can check that each time you combine diagrams, you get a new diagram that's in the same set. You will also find an identity element, and you will also find inverses for every element. As examples of other finite groups, we can consider, for example, a subset of permutations that has an even number of odd cycles, not odd cycle meaning of cycles of odd length. That's a subgroup. If you take products of permutations with even number of odd cycles, you obtain permutations with even number of odd cycles. Also, a subgroup is this cyclic subgroup. So you take single, let's say, k cycle, and you just take products of with itself. You just you wrap up around a kind of k order k set, which is the different powers of it. So if you take a k cycle and you take it to the power k, you return to the identity, and it's a closed subset of order k and a subgroup, and it's abelian. Any questions here? Okay. So we presented a finite group called the symmetric group. Now we will present another example of groups, in this case, sets of matrices and their matrix product being the operation, the group operation. So for example, the set of all invertible D by D matrices, so the ones that have non-zero determinant, is a group. If I take two invertible matrices, I will get an invertible matrix. Every invertible matrix has an inverse because it's invertible, and so on and so on. It's called the general linear group. Of course not, I mean, again, if I don't impose this condition of invertibility, the set of D by D matrices is not a group. Okay. Stuff doesn't, like, if, like, I will not have inverses. Okay, definitely. Like an important subgroup for quantum computing of the general linear group are those invertible matrices that are also unitary, meaning that the inverse is essentially the complex conjugate of the matrix. This implies that the determinant of this matrix is basically a complex number with unit modular. Okay, modulus 1 complex number. This that u is e to the I phi, and there's yet a subgroup of this unitary group that's a special unitary group that is those unitaries that also that where this complex number is just 1. It's not, it's like you get the phase that is 0. Okay. So let's exemplify. These are the Pauli matrices, like identity, but then I'm putting Ix, Iy, Iz there, and I claim this is a subset of SU2. All of these matrices, so the phase X, Y, and Z, and identity, all of these are elements of SU2. To see that, we need to test whether they have determinant 1 or not, essentially. A little kind of trick is that one can use is that if I want to compute the determinant of a scalar times a D by D matrix, this is the scalar to the power D times the determinant of the D by D matrix. So the determinant of, I don't know, Ix, since it's a 2 by 2, is I squared times the determinant of X. The determinant of X is minus 1 times I squared is 1. And we can check that all of these matrices in this set here are in SU2. Okay. Instead, like I times the identity is definitely not in SU2. It's in U2. As an exercise, we can check that all of these, for example, are groups. Like Ix composed with Iz is Iy, and Iy is in SU2, and so on and so on. We can play this game of checking group properties. So all of these GL, U, and SU are matrix groups that are Lie groups, but not all matrix groups are Lie groups. For example, we can take general linear or unitary or special unitaries over finite fields, and we will get finite matrix groups that are not Lie groups. Okay, but we will not work with this. I just want to mention. Are we good so far? We have exemplified 2 groups. Okay. So we made it to representations. A group has a well-defined product. So basically, a group can act on itself, right? Even via this product. And a representation will essentially enable groups to act on vector spaces. Okay, we will call these group modules, a vector space that admits an action of a group. And the way we do this is we map in a certain kind of not arbitrary, constrained way there will be conditions on the way we map group elements to linear operators, essentially invertible linear operators on this vector space. So formally, a unitary group representation R is a map from G to the unitary group on the vector space V. Those are two groups, G and UV, as G is by definition a group, by assumption, and UV is, we just saw it's a group before, right? And the condition that we impose on this map is that in equation 1, like the map preserves the group structure. If I compose G1 and G2 and then take the map, or I first map and then compose these operators on the image, I get the same thing, okay? This doesn't mean that the image of R, so the subset of UV where the group gets mapped, is isomorphic to the group. There could be a kernel, so the map doesn't need to be injective. As I'm saying, the image of R doesn't need to be G. The kernel is a subset of the group that gets mapped to identity. If, of course, the identity gets mapped to identity matrix, the identity of the groups gets mapped to identity matrix, but if something else than identity of the group gets mapped to the identity, this is it will form a larger than order 1 subgroup of the domain, and it will kind of indicate that the representation is not injective or not faithful, as it's typically called. Not too important. I think it's nice to realize this. In fact, there's kind of a like maximally non-injective, maximally non-faithful representation every group has, that is called the trivial representation. Well, the whole group, this representation is one-dimensional, and the whole group gets mapped to the number 1, essentially, and this is a representation. Whole group gets mapped to the 1-by-1 identity matrix. And you can test that this satisfies all, for any group, this satisfies all of all the conditions of representations. I hope, are we going okay? This is clear. Okay, representation is a map that allows groups to now be embedded into unitary matrices. So examples of representations are the standard representation of UD, right? UD is already kind of matrices. So we map matrices to matrices by like literally the trivial mapping, which matrix U gets mapped to itself, okay? And this is already kind of a representation because now you can act on CD, okay? But the map is trivial in this case, of course. Now, like a jump of complexity, like the unitary group of degree D also has interesting representations on this kind of completely symmetric and completely antisymmetric subspaces of the tensor K power of CD, which describe particle preserving free fermionic and free bosonic operations on D modes with K particles. Jump of complexity, but it's also a representation of UD that may be of interest to physicists. Okay. Yeah. Now we'll describe a family of representations called permutation representations. Essentially, whenever the group has an action on a set X, we get a representation straight away that is a representation on the free vector space corresponding to that set. The free vector space is a fancy way of saying that I have a vector space where each set element is assigned a linearly independent direction. Okay. For example, like the computational basis of n qubits is the free vector space of the set 0, 1 power n. Okay. Okay. So if G has an action on a set, again, all I need to do is like define the R of G on X, sending like, again, sending the computational basis element X to a new computational basis element, G circ X, which is a new set element by definition. So this representation is just basically permuting the computational basis. That's why it's called permutation representation. And all of these kind of, let's call it D by D matrix. Let's call D the order of the set. All of these D by D unitary matrices R of G are not only unitary, they are just like permutation matrices. A permutation matrix, it's gonna say it here, it's just a matrix with a single one per row and column, and the rest zeros. And again, it's just a relabeling of the basis, a permutation of the basis elements. Yeah. So here I explicitly write R of G is unitary operator as sending X to G circ X for every X. You can check these are representations, these are unitary, all of the things that you want to check about groups and reps. There are d factorial many such, so in okay, in a vector space of dimension D, on a vector space of dimension D, there are d factorial many permutation matrices, but of course, we are embedding G into this, which we hope, I mean, if we want the representation to be injective or faithful, we better have that order of G is less than d factorial, okay? I mean, only if we want injectivity. It's not that we need to want it. So examples of permutation reps. Of course, Sn has an action on the set n, the set of n elements. All you need to do is like come here and you want to ask where. So think of this as the computational basis now. Like there are n elements, and if you want to see where like the second element is being sent by your permutation, you just follow the line, it's going to the first. So sigma on state 2 will give me 1, and so on. And here I'm writing, for example, two kind of explicit matrices for permutation 1, 2 and permutation 1, 2, 3, 4, okay? So again, the way to read this is that the permutation 1, 2 is sending, you know, see, like, look at the columns. This is the first state of the computational basis. This is the second, this is the third, and this is the fourth. It's just reordering these things. And the same you can see in the other one. Yeah, okay. Other options for this set are the set being the symmetric group itself, right? It's a set, right? Before being a group, the symmetric group is a set. So and the operation is just the group operation. Other choice is the kind of the set of n qubits, or like words of length n on an alphabet with q elements, basically. And the way to act there is by permuting the letters of the words. And when we use this set, the vector space we get is the n-qubit vector space, and the representation is the permuting qubits, okay, which we will come back to. Any questions here? Okay. This one? Yeah, excellent. Exactly. This is a cycle. This is a cycle. Each time I do a kind of bracket thing like this, I mean that 1 goes to 2, 2 goes to 3, 3 goes to 4, 4 goes to 1. Yes, yes, yes. Like here is the same, 1 goes to 2, 2 goes to 1, and 3 goes to 3, and 4 goes to 4, but I omit them. Okay, great. We move on. Okay, maybe the fundamental result in representation theory is that representations have like essentially a unique decomposition into building blocks that are called irreducible representations. Before explaining what it is, like think of an integer. It has a unique decomposition into primes, right? Like an integer n is always, you can always write it in a unique way in terms of like the first prime to some power, the second prime to some power, the third prime to some power, essentially. This power is essentially how many times this prime appears in the integer. It's called like a multiplicity. Something similar will happen with representations. Each representation will be decomposed into these irreducible representations with certain multiplicities, up to isomorphisms, which are not very relevant at the moment. Okay, so back to our notation. R is a G-rep, B is a G-module. We say this pair of like RB is irreducible if there are no invariant subspaces. Proper here I mean like non-trivial. Invariant subspace W of B such that they are invariant under the action of G. By invariant, again, like, I mean, I cannot find a subspace of B such that when I act with all group elements, the subspace is preserved. As examples, like we can ask if the representation for S4 on 4 elements set that we just saw is irreducible or not. The question is, can we find a subspace of C4 that is invariant under the action of S4? And the answer is, well, it's not irreducible because there is such an invariant subspace, say uniform superposition over like the computational basis of C4 essentially. And you can see like since I know one will be mapped to some other guy, and like since it's a permutation, like it will be a relabeling, and if you have a uniform superposition and you act with a group, you will still have a uniform superposition. So this line, one-dimensional line W is invariant. Therefore, it's a subrepresentation. Therefore, like B was not irreducible. Every time you find a subrepresentation, the complement is also a subrepresentation. When you're working with the complex numbers and finite dimensional representations, which is what we will stick to in the whole course. So, okay, so we now found two invariant subspaces, W and W perpendicular, which are subrepresentations. And we can ask again if these are irreducible, and we can try to verify that they are. We will later see how to compute or like verify or test if a representation is irreducible or not. The change of basis from the computational basis to a basis that accomplishes this direct sum of vector spaces. So for example, now the first kind of basis element would be this kind of, I don't know, the sum over I of I, and then I choose a basis, I have it there, right? I choose a basis for W perp. In this new basis for V, the matrices of the group look block diagonal. The first block is 1 by 1, the second block is 3 by 3. Okay. And as I was claiming before, every representation will always be able to be decomposed in this way into blocks that are irreducible in a unique way, in the sense that the multiplicities of each irreducible will be unique. And of course, you have freedom in choosing bases within the blocks. But this is not the point. Something we will, I will try to kind of argue is that the basis where this thing looks maximally block diagonal can be called a Fourier basis for this group representation, and U can be called a Fourier transform. We will get back to this, but it's nice to have this in mind. So more generally, any rep, as I was saying, there's a U that will take me to this kind of form where I have a big direct sum of big blocks, and in each of these blocks, let's say labeled by some gamma, I will have the same matrix repeated m gamma times. Okay. This is too much, this is okay. So notationally, I have first a direct sum over gamma, and then this matrix R gamma of G, which is the irreducible representation, tensor identity m gamma, identity m gamma. When I tensor a matrix with identity, I just get this matrix repeated the number of times corresponding to the dimension of this identity matrix. Starting to freak out. Oh no. I can just move, okay. Yeah. This is a note for the future, is that whenever I have matrices of the form some arbitrary A, let's say D by D A tensor m-dimensional identity, it's easy to describe all the matrices that commute with this set of matrices. Anything of the form identity of D, where the A is acting, tensor a B that is m by m. So these two sets of matrices are mutually commuting. Okay. So, all right. We know what the irreducible representations are, and now we may ask, how do we create representations, essentially? If we have representations, how do we get new representations? A kind of a boring way is to stack irreducible or stack representations like side by side as a direct sum. But a more interesting way is to take the tensor product of the representations you have. That's like put reps on different subsystems. Okay. It's fine, I think. Like we'll try it like this. Okay. So we have two reps. Let's say R alpha and R beta. Oh no. Yeah, okay. There it is. It's okay, I think. Sorry? Any questions? Okay, the tensor product of representations. Given two representations, we can take the tensor product that is defined, it's a new representation. Again, from G to now the tensor product of the group modules for each. You can test this satisfies, if those two were representations, the tensor product satisfies everything that needs to satisfy to be a representation. But more importantly, the irreducible decomposition of the tensor product in general exhibits irreducible representations that were not present in the originals. If like alpha and beta were irreducible, B alpha tensor B beta is typically not. Okay, and again, it in general contains new representations gamma with certain multiplicities m gamma alpha beta. Record how many times gamma appears in the tensor of alpha and beta. These multiplicities are called, for the unitary group, Littlewood-Richardson coefficients. For the symmetric groups are called Kronecker coefficients. Very interesting mathematical problem to compute them. Very hard one. We have a talk on the workshop for this, but and we may come back later. Yes. So besides the multiplicities, again, you may ask, who's the Fourier transform that takes me to the explicit block diagonal form? And it has a name called Clebsch-Gordan transform. Okay. Again, explicitly here is this unitary that maps me when I take two irreps. Essentially, it's mapping the uncoupled basis, which is labeled by, let's say it was alpha and beta, and then we have an index I alpha and J beta for the basis elements on each of the irreps. Now I take the tensor product, there's a kind of a basis that's coupled, that instead is kind of gamma, K gamma in the different options on D gamma, and a multiplicity label, T gamma alpha beta. So we can map between these two bases, and the mapping between these two bases is called the Clebsch-Gordan transform, which is a Fourier transform. In particular, then the Clebsch-Gordan transform was used long time ago to build yet another Fourier transform called the Schur transform, which we will talk about soon, which is essentially the Fourier transform that block diagonalizes the qubit permutation and the local unitary action on every qubit and qubit permuting action of Sn. When you diagonalize this representation, and the reason why you may want to diagonalize this is many kind of tasks in quantum information. For example, spectrum estimation. You have many states that are kind of, you have like the same state repeated in different registers. This is permutation invariant, right? Because it's the same state. And you also care for a task. You want to estimate a property of the state that is invariant under unitaries on each register, like the spectrum of the state. So the correct thing to do here is to have a transformation to basically like remove all unnecessary information. And again, the unnecessary information here is the permutation information and the unitary information. So the Schur transform will be super handy for this kind of tasks. Okay, an example of the Clebsch-Gordan transform and rule is the following. 2 qubits, okay, like 2 spin 1/2s. Like we know in general, like irreps of SU2 are labeled by spin, half integer spin, and the dimension of the spin S is 2s plus 1. And if you tensor S1 and S2, you get all possible spins between S1 minus S2 and S1 plus S2 with multiplicity 1. Again, this is non-trivial. In principle, you could have multiplicity, but from physics class, we know that it doesn't happen here. In particular, if we take S1 and S2 to be 1/2, we know that this is coupled to 0 and to 1. And these 0 and 1 are irreps in the coupled basis. The 0 is a singlet, one-dimensional subspace. The spin 1 is a three-dimensional triplet, so on, right? This is just an example of the previous slide where I was explaining how when you tensor irreps, you then get new irreps. Here you tensor 2 spin 1/2s, and you get a 0 and a 1. These are new irreps. Okay. Questions? No questions. I want to kind of lay down this question of how do we know if a rep is irreducible, and how do we compute these decompositions? we will try to answer this later. Okay. All right. Okay, let's define algebras, or like C algebras. It's a similar idea like a group, right? But now, instead of having a set, you have a vector space. And because it's a vector space, you're allowed to add elements. Like group is a set, you cannot add group elements. You can multiply them. Here, you have a vector space, so besides multiplication, you also have addition. And you have like scaling and linear combinations. The price to pay is that you lose inverses. But that's okay. So, as I was saying, it's an algebra is a vector space that has a product, like a group. The product is bilinear. It doesn't make sense to ask for linearity on the product of a group because, again, the group is not a vector space. Like a group, it has an identity, and if we demand it's a star algebra, this star means there's an involution. It's just a map that when you apply it twice, you get back to the same element that you started with. Kind of similar like an inverse, but it's not an inverse. Okay. Like it doesn't, like an inverse, you apply it twice, you get back to the same thing, but you also have that an inverse with an element gets you identity. That's not true for the involution. Okay. Even algebra, subalgebras are closed subsets under linear combination and products. There's a concept of a center that's kind of the things in the algebra that commute with everything else. And we will exemplify algebras and with two basic, we will pay attention to these two interesting algebras. One is the group algebra of a finite group, and the other one is the algebra of linear operators on a vector space. Let's go there. So given a finite group, we define the group algebra as the vector space with like formal basis being the group elements. We already did this with the set, right? So it's the same idea. The only difference with a set is that we also have, in this vector space, we have a product now, which is kind of the group law. Dimension of the vector space is the order of the group, and the group is the basis of this vector space. Any representation from G to unitaries on a vector space V will extend by linearity to a representation of algebras. If we now replace like the domain by the group algebra and the codomain by the endomorphism algebra on a vector space. And yes, like as I said before, so the linear operators on a vector space are not a group, but are a C algebra. Multiplication is the matrix product. I already defined the center of an algebra. Now I'm defining the center of the group algebra. Again, the things that commute. If you take elements of a conjugacy class and you add them up, you get an element of the algebra that is central, so it's in the center. And in fact, it's a basis of the center, and therefore the dimension of the center is the number of conjugacy classes. Some other central elements will come from characters. A character is just, for any representation, you can define the character to be essentially, remember, representation is a map from the group to unitaries on a vector space. A character is a map from the group to complex numbers. It's just essentially composition of maps. You first map to the unitaries, and then you take the trace of the unitary. Because the trace is invariant under conjugation, the characters are class function in the sense that they only depend on the conjugacy class of the group element. There's an inner product on this space of class functions, essentially the center of the group. And I think the most important thing to see here is that if you consider the characters that arise from taking the trace of irreducible representations, they form a basis of the center of the group algebra, and most importantly, they will allow us to basically compute the multiplicity of any representation. If we have access to evaluating the character of a representation, we can compute the multiplicity of any irrep by taking the inner product of the character of R with the irreducible character, gamma. Let's see why. So we call in chi gamma the irreducible character associated to irrep gamma. We define this central element, E gamma. It's an idempotent in the sense that it's squares to itself, and they are also orthogonal, and they add up to the identity element on the group algebra. Again, just pay attention to the definition. Sorry. Again, it's just like a weighted sum of group elements, and the weights are just the evaluation of the characters, basically, of the irreducible characters. If we now send this group algebra element through the representation, we get this thing I'm calling pi gamma, which is a projector. It's a linear operator that is, again, like it's squares to itself, and its trace will be the dimension of the whole. So it's a projector into the whole isotypic containing all copies of the same irrep gamma in B. That's the claim. As I'm saying here, like isotypic, the gamma isotypic component is the subspace of B, or the subrepresentation that is the collection of all irreducible representations gamma. So all M gamma copies of it. And I'm claiming that this projector, the projector here is just the sending this central element E gamma through R. And for example, if you, since from that equation, if you take the trace of pi, you should get M gamma times the dimension of each B gamma, so D gamma. And if you want to know M gamma, you could just like take the trace and divide by D gamma, and then you got that equation. But that equation, you can remember, I mean, the D gammas cancel, and that's the inner product of characters. So as I was saying in the previous slide, M gamma is just a component of the character of R on the character of the irreducible character gamma. Yeah, so this is just to say how to compute. This is not super efficient way, but like, again, it's a way to do it. How do you compute the composition of an arbitrary representation given access to the matrix, to the matrices, let's say? For each gamma, you can compute M gamma by building this pi, by summing over the elements, weighing with the irreducible characters, taking the trace divided by D gamma. Or alternatively, if you can evaluate chi R, you can use the kind of inner product. Okay. Commutants. Given two vector spaces, we will describe, or we will call VW, the algebra of linear operators from V to W. And if V is W, then we typically denote it end V, as we were already doing, right? These are the, if B is D-dimensional, these are the D by D matrices, complex matrices. If V and W are also G modules, we can consider a subalgebra of all linear operators that are, we select only those that commute with the group action, as defined here. So this new set with a G G VW is those A in VW that satisfy the equation on the right, that is kind of for all group element. If I conjugate, I get the same thing. They essentially commute with the group action. And this is similarly defined for end V or and GB will be the invariant operators. And this is called the commutant. We'll have a lot of applications, as we will see soon. I think this is not very important. All I'm saying here is like, you can consider itself as a G module with a given representation explicitly, like this RG is just like this RW conjugating on an RV on the sides, and in this sense, the operators that remain invariant are those that. So all I'm saying is the commutant is the invariant operators, basically. It's interpretation. Okay. Schur's lemma states that if you have two G modules, V and W, that are irreducible, the only G invariant maps between V and W is the identity isomorphism if V is isomorphic to W or nothing. The only way to map between group modules is to kind of map irreps to irreps. That's what Schur's lemma says. The implications are that if we know the irrep decomposition of P and W, explicitly say like B has irrep alpha M alpha B times, and W has irrep beta M beta W times, then we know the commutant. We know exactly which are the invariant operators because we use Schur's lemma. So equation 2, we just explicitly expand what this is, but then we use the fact that G of two irreps can only be the delta from alpha to alpha. The beta there should be an alpha. So basically, this is saying that for each irrep that it's written here. Now take the dimension, and you get sum over alpha M alpha B M alpha W. There is one element in the commutant per pair of irreps alpha in B and in W. Again, this is I said it in the beginning. The only way to map G invariantly between G modules is to connect irreps with irreps. If in particular, like the two modules are the same, so we're looking at like linear operators on B. This is what we get. Again, we get a direct sum over possible irreps alpha, and we get identity where the group was acting, and we get arbitrary stuff in the multiplicity space. If you recall that the group element, this is what I'm trying to say, a group element just looks like certain irrep repeated a number of times. The things that commute with the group look like identity where the group was acting and arbitrary stuff in the second register, essentially. A commuting operator must be trivial where the group acts non-trivially and arbitrary where the group acts trivially. If, in particular, B is irreducible, then we had this equation somewhere. Yeah, the dimension is just sum over alpha M alpha squared. But if there's only one M alpha that is 1 and the rest are zeros, the dimension is 1 squared, that is 1. So that's an easy way to test if a representation is irreducible. Compute the dimension of the commutant. We will soon see how to compute the commutant. Once you know how to compute the commutant, you can compute its dimension and test if it's 1, it's an irreducible representation. If it's more than 1, there has to be more than one irrep. If you take the dimension of the center, this will tell you how many irreps there are without counting multiplicities. The double commutant theorem is this kind of very general result, which Schur-Weil duality is an instance of, that says that if you consider, again, take the group algebra and embed it into NV and call it A. And now use C for the invariant operators. That's also a subalgebra. So we now have two algebras, A and C. Again, A is mapping group elements, group algebra elements into linear operators. C is the linear operators that commute with the group. The double commutant theorem says that the things that commute with the things that commute with the group are the image of the group elements. And analogously, the things that commute with A will be essentially C. It looks kind of tautological, but it's not. It's an interesting result. And the reason is, again, what I was saying before, the stuff that comes from the group has a structure that is kind of certain dense block repeated many times, and the way to kind of commute with this is to have the opposite or the dual kind of structure. Be trivial where this is non-trivial, and non-trivial where this is trivial. And we made it to basically the instance that we are most interested in, which is these two groups and the corresponding algebras. So again, symmetric group on the n qubits, and the unitary group acting locally or diagonally on all the registers at the same time with the same kind of unitary U tensor n. Let P be the algebra in the image of the group algebra of Sn, and Q be the algebra in the image of the group algebra of the unitary group. The claim is that these things are mutual commutants. Permuting stuff commutes with acting locally, and acting locally commutes with permuting stuff. And not only that, is everything that commutes with permuting stuff is a local action, or is a linear combination of local actions. Okay. And besides that, there's this also kind of equivalent version of Schur-Weil duality, which will take us kind of to understand. We will need more representation theory, but essentially says that the group module, or like this n-qubit register, splits into irreducibles of Sn and W in this coordinated way. The same irreducible, the same label lambda appears on both sides at the same time, this kind of tensor. In general, like this could, like, this doesn't need to be the case, but we will see this is the case, and this lambda is a mysterious label we will soon understand. Okay. How are we doing on time? 15 minutes, right? Okay. Any questions? Okay. Too fast, too slow? Yes, all I'm saying is, if I think of a product group, I call it G, which is this direct product. If you take two groups, you can consider the direct product group, which is essentially the ordered pair of elements of each group. As a module for this group, it decomposes into these T gamma that are irreducibles of these groups with multiplicity 1. This is the Schur-Weil duality statement. But we need to understand who V lambda and W lambda are in order to kind of understand these equations. But besides assuming that we understand those, one can already see that using this equation, you can elegantly describe or characterize the Sn rep P or the UD rep Q by restricting G to those two groups. Let's see why. Suppose I now take equation 4 and restrict to the subgroup of G that is just Sn, meaning kind of the group action that I'm considering is just making the unitary group go away trivially. what will happen is that the W lambda will now become basically copies of, or like it just becomes C of the dimension W lambda, because it's not there's no unitary group action anymore. The irreducible representation of the unitary group essentially gets converted into copies of P lambda. So if we know the dimension of the unitary group reps W lambda, we immediately know how many times the Sn irreps appear. That's the power of Schur-Weil duality. Again, we need to understand who these are. A small note on how to compute the commutant in practice, not efficiently, but again, like it's good to have at least a way to do it, is the following. Find a generating set for the group. So these are k elements such that any element can be written as a product of these k elements. And then the claim is that the commutant is just the intersection of the commutant of each element. Well, the commutant of like a matrix are essentially the linear operators that commute with this M, basically. So all we need to do is compute the commutant of each generator and take the intersection. And to solve this equation, we can vectorize using this law of vectorization, and we try to keep, so we want to vectorize commutant of AM, which is AM minus MA, or like ARG minus RGA. When we vectorize and pull the vec of A to one side, we get this. We essentially find a d squared by d squared matrix that is RG transpose tensor identity minus identity tensor RG transpose. We literally, if we know RG, we can compute this as a very big matrix and find the null space, and those are the A that commute with that thing. You repeat this for all the group, the generators, and you take the intersection. Again, the way to compute the null space, you can do it like numerically with SVD and so on. This is polynomial in dimension of V. Then you take intersection, you found the commutant. I think it's good to know how to do it. It's not very efficient. Okay. A little bit of symmetric group rep theory. There's something called integer partitions that play an important role at labeling irreps of Sn, and UD is this mysterious label that we saw. So let's jump right into it. For an integer n, a partition of n, and it's written like with this little symbol, is a sequence of weakly decreasing positive integers that add up to n. These are examples of partitions of 4. There are 5 of them, and it's just a way of writing 4, again, as a sequence of weakly decreasing positive integers. So 4 is, for example, 4. That's the first partition. But 4 is also 3 plus 1. That's the second partition. 4 is also 2 plus 1 plus 1, and so on and so on. Or 1 plus 1 plus 1 plus 1. Okay. The things on the right are called Young diagrams, are used to represent partitions graphically. And it will be important later to consider a subset of the set of 4 partitions that have a fixed or up to some length, let's say D. So for example, there's only one partition of 4 with at most one part, which is the first one. But there are 3 partitions of 4 with at most 2 parts, which is the first, the second, and the third, and the fourth. Okay. For each partition, the claim is that there is an irreducible representation of the symmetric group. We call it R lambda, the homomorphism, and B lambda, the vector space that is the irreducible group module. each time you have a, a representation, you can choose to evaluate it on a subset or a subgroup of elements. And when you do that, this is called restricting the representation. Whenever a representation is irreducible and you think of it as a representation of a subgroup, it need not be irreducible anymore. Okay? It may split into more than one stuff. Okay, so we will consider the restriction of the irreducible lambda into the subgroup Sn minus 1. That's the subgroup of Sn that fixes the last element. For example, 1, 2, 3, 4 of S4 doesn't fix 4, but 1, 2, 3 and 4 on its own does. So the second, this 1, 2, 3 cycle belongs to this S3 subgroup in S4. There's this rule called Young's rule that asserts that when you restrict the irrep lambda into Sn minus 1, you get certain irreps of Sn minus 1 with multiplicity 1, not more than once. Okay? And we can take each of the irreps that appear on the right-hand side and restrict to Sn minus 2. And again, it will be multiplicity free. And we keep doing it until we reach the trivial irrep of the trivial subgroup. Okay? By doing this we kind of essentially can think that we are following a path in this kind of diagram of partitions. At each level, we have a partition of like n, n minus 1, n minus 2, and so on, which corresponds to a choice of an irrep of the corresponding subgroup. So you start from a leaf and you start making a path down, or you can consider, like, again, like constructing the leaf from the empty partition. Anyways, it's the same. And we will use T to label this path. Here are two paths that lead to the kind of the partition 2, 2. For example, I can go first to 1, 1, then to 2, 1, and then to 2, 2. But I can also go first to 1, from 1 to 2, and then to 2, 1, and then to 2, 2. So these are the two paths that are in the middle, essentially, that branch first. I don't know if I have something to point. Yeah, here. I can go this way or this way. Two different paths. Paths can be also described by placing number of the on the resulting on the leaf partition. The number is just saying at each instance what's the kind of instantaneous tableau for a partition. For example, if we want to see where do we branch first, we just remove the fourth and we have this guy. And then we remove the 3 and we have this guy. So this thing is going through this path. Instead, this one is going through, remove 4, remove 3, and you have this 1, 2. So you have the diagram that is like the two boxes on the first row. So it's saying that you're going through this path. Okay, why do we care about paths so much? It's because paths are a canonical basis for this irreducible representation. Just because, as we're saying here, if you take dimension on each side, and since the dimension of this is 1, then you get a summation. You get a summation over paths. So the dimension is just the number of paths. And you can literally associate each path with a unique basis element of the irreducible representation. I'm saying there's an efficient formula to evaluate the number of paths. Super cool. This is not in general true. So we can compute the dimension of the irreducible representations of Sn with this kind of formula, where like the thing on the bottom is basically the product of, in the partition, go to each box and count the boxes that are below and to the right. And then you take the product of all cells of this number, and you divide them factorial by that, and you get a dimension. Yeah, as I was saying, like the paths give us a basis for the irreducible representation. All that it remains is to explicitly build the irreducible representation matrices So how the group acts on each path. Okay. To do that, we choose yes, of course, partial order. There are we can discuss this. There are kind of many possible ways of ordering the space of Young diagrams. There are more than one way. Yes, we can try to discuss this later. So we will build the reducible matrices. Again, this means for each group element, find the d lambda by d lambda unitary matrix that embodies the representation. The trick that we will use is that it suffices to build the matrices corresponding to a generating set for the group. Because if I build matrices for generators, then any group element will be the representation, the product of the matrices for each generator. I hope this makes sense. Like, again, it's pretty simple idea. So let's represent this generating set. Like Sn is generating, so any permutation can be written as a product of adjacent transpositions. So we will need to represent the adjacent transpositions. And yeah, the claim is that the action is extremely sparse. Like the adjacent transposition on a tableau essentially puts a face on my tableau and potentially makes another T prime appear. Only when T prime that is defined like here, like with again, like I don't think it's necessary. We can like you can take your time to understand exactly how T prime is built and how these distances are built. Never mind. I think the important point is that every basis element is mapped to at most two other basis elements, itself and another one. Potentially not. This may be zero whenever T prime is not a valid tableau. Yeah, and so essentially in the span of these two paths, the representation looks like a reflection on a plane. Essentially like X and Z operators with these kind of coefficients that are kind of a rotation angle that depends on the tableau and on I. Yeah, so we've broken down these representations into kind of these little 2x2 blocks, orthogonal matrices. Here's an example. I think we can I can upload the slides and you can work it out. But I'm building basically the matrix for 1, 2 on S3 on this irrep of S3. So then you can also build, whoa, interesting. No, not bad. Okay, I build this one, you can build this one. Once you build this other one, since 1, 2, and 2, 3 are all generators of S3, then any of the 6 elements of S3, you can find the 2x2 matrix that by just again, mapping, decomposing it into 1, 2, and 2, 3, a product of those, and then taking a product of generators like this, okay? An exercise. Should I go or not? Okay. Are we okay with 5 minutes? Let's see. Okay, we describe the representation theory of the symmetric group. The representation theory of the unitary group is, we will see it's labeled also by partitions, okay? So we remember that this was a standard representation. It's a kind of the trivial map between unitary matrices and themselves. Now you can also take the action on the tensor of CD and CD And this will basically break into irreducible representations with like the symmetric and antisymmetric subspaces. As I was saying, just like with Sn, we use partitions to label SUD irreps. The difference is that we now put a little kind of constraint on the length or on the number of parts of the partition, and we remove the constraint on the n, the number of boxes. Like literally, we can like have arbitrarily large number of boxes in a partition, and it still labels a representation of UD. But the real constraint is that the number of parts, so the rows, must be less than D. So for example, all of these are representations of SU2, therefore spin representations with 4 boxes, right? So the way to read what's the spin, again, like SU2, it means that the diagrams that the Young diagrams that, or the partitions that label irreps of spin must be at most 2 row. Okay, so here are kind of like 3 different 2-row diagrams with 4 boxes. How do you map a diagram to the spin? All you need to do is first row minus second row divided by 2. That's the spin. So for example, this one is like 4 minus 0 divided by 2, 2. That's a spin, spin 2. So this irrep is a spin 2, so it's 5-dimensional. This is spin 1, and this is spin 0. Okay. Yeah, fun fact is that like any and all partitions with n boxes appear as subspaces in CD tensor n. So if you want to produce kind of these spin irreps, you could take 4 spin 1/2s and then choose the right subspace. Okay. Again, and it makes sense, right? Like we said, like 4 spin 1/2s, and we said like the largest spin that we were getting is 2. It makes sense, right? Like in general, if I take like 100 spin 1/2s, I will get 50 as the spin, the largest spin that I can get when they are kind of, they all couple to like additively, let's say, to S1 plus S2 plus S3 and so on. 1/2 plus 1/2 plus, okay. Yeah, okay, I think it's clear. Yeah, and here I'm also claiming that for every isotypic subspace of CD tensor n, isotypic for the action of Sn, it will be an isotypic for SUD2, and that's kind of what sure duality says. But in a sense, it's a little bit like saying that I said here that this guy will appear as in the tensor n of CD. What I'm saying is it not only will appear, but it will appear in the as a kind of a symmetrization over lambda of the Sn rep. This is an Sn rep, right? So for example, like this one, I think I say it here. Yes. If we want SUD reps of type like lambda equal like the kind of the partition with like only 1 row, we can take this subspace, which is a subspace of CD tensor n, which is a symmetric subspace, and that will be the SUD rep. So another way to say it is the spin 2 irrep is the symmetric subspace of the tensor of 4 spin 1/2s. Okay. Okay. All right. We do the same thing that we did for the symmetric group. We find okay. We first kind of claim that like B lambda is an irrep of now of SUD. And we start branching to down subgroups. Again, SUD minus 1 is the submatrix that has a 1 on the last row and column, and then is dense unitaries on the D minus 1 by D minus 1 block. That's a subgroup isomorphic to SUD minus 1. When we restrict, literally in the same way that happens for Sn, these irreps branch multiplicity free, so we can do the same game, play the same game, and use paths to label basis elements of SUD reps. The paths will be longer. Before they were kind of n, like length n, and now are length d. Okay, well, longer it depends, but in principle longer. Again, I don't think it's necessary to go in much detail. Like one usually uses this kind of patterns to label the paths, but again, it's the same. Like each row represents a choice of a partition labeling an irrep in the path of restriction, in the chain of restrictions. Here are some examples. I start from like the standard irrep, and these are all possible paths down. That's why I get the standard irrep of SU3 is three-dimensional. There are 3 paths. Cool, like it makes sense, right? Now, another irrep of SU3 is the one that has like 2 boxes, right? Start, and then you branch all the possible ways. I use colors here. I get 5 elements. This is the adjoint. Is the adjoint? Yes. No. No, it's not the adjoint, sorry. It's just a symmetric subspace of 2. Adjoint is 8-dimensional. Yeah, and here there's another irrep. These are all irreps of SU3. All right. And final thing, okay, I don't do it, but you can also, again, use this choice of labeling of bases and then find how the group acts on these paths and find the matrix and find the matrix representations, generators, and then so on and so on. You need to go through Lie algebra to do that, and I'm not going to do it here, but it's essentially the same idea. And yeah, we made it to the wrap up. This is the last slide. We now revisit Schur-Weil duality. We learned the representation theory of SUD and SN, partitions label irreps of both, and this mysterious kind of label that I had here is just now the sum is over partitions of length d of n. Okay, and if we, for example, introduce a formula for the number of paths in the branching of SUD from lambda, it's given by this thing, you can now characterize how many times the qubit permuting representation, how many times the irrep lambda of Sn appears in the qubit permuting. That's this dimension. So you can go and for example, test and find out, like, describe this qubit permuting representation in great detail. In principle, you need to verify that this is the case. For all of these partitions, the product of dimensions of SUD and Sn, and then you sum, this should be d to the n. Okay. I think we can wrap up with this. We've introduced representation theory of groups, algebras, and exemplify with symmetric and unitary groups. We will see applications soon. As I was saying, like the reason why they're interesting is that like they have this kind of commuting action, and the ability to efficiently compile transformations that block diagonalize these actions, known as the Schur transform, will have important impact and application in quantum algorithms. With that, I thank you.